Module 4, Lecture A, Performance Metrics. By the end of this lecture, you will be able to compute descriptive measures for production and process performance data, calculate utilization, throughput, yield, and downtime metrics in Python, and interpret metric results in relation to process improvement decisions. Descriptive measures. Mean metrics. Mean metrics help engineers reduce performance data to one clear typical value, such as average output or average cycle time. This makes it easier to track trends, compare results, and understand overall productivity despite daily or shift-to-shift variation. Engineers can also use these averages to estimate capacity and labor needs. Mean values are useful when the data is fairly consistent because they can show the center of the data clearly. But extreme values, such as a long machine stoppage caused by wear or operator changes, can pull the average away from what is typical. This does not make the mean incorrect, but it does mean the result needs context. To interpret a mean well, consider how the data was collected and whether unusual values are meaningful events or errors. Mean metrics provide a useful baseline for comparing current process performance with desired results, such as average waste or average workflow time before and after a change. They help engineers and managers judge whether improvements are working, but the mean alone can hide outliers and variation. For that reason, averages are treated as a starting point for deeper analysis of stability, improvement, and risk. Python code. Mean metrics. Mean metrics describe typical engineering performance, but they should be interpreted carefully. Small datasets make the calculations easier to check, while unusual observations provide important context for understanding what the average really means. We begin by importing NumPy, a Python library for efficient numerical computing. It helps manage datasets and calculate statistical metrics, making it useful for analyzing engineering performance data. We store 6 hours of production output in a NumPy array, with each value representing the units produced in 1 hour. This structured numerical data makes it easy to calculate useful metrics such as averages later on. Cycle times for repeated assembly tasks are stored in a NumPy array, with each value showing the time in seconds for one cycle. These measurements help evaluate process efficiency and consistency by supporting average calculations and spotting unusual cycle durations. The code first confirms that both data sets contain at least some data before doing any calculations. This prevents later errors that would occur if the processing assumed missing data was available. If either dataset is empty, the check stops the program and alerts the programmer to the problem. We find the average production rate by taking the mean of units produced per hour, giving a typical output level. We also take the mean cycle time to estimate how long each cycle usually takes. Together, these averages give a quick view of overall production line performance. To estimate a typical cycle time, keep only cycle times under 50 seconds and calculate their average. This removes unusually long cycles caused by stoppages or anomalies, giving a more representative value. The output reports 3 key production measures: average units produced per hour, average cycle time, and typical cycle time without unusually long stoppages, each rounded to 1 decimal place. The main takeaway is that stoppages raise the overall average cycle time, showing how outliers can distort mean values. This script uses arrays to summarize production line performance. It first confirms the production and cycle time data are present, then calculates the average units produced per hour and the average cycle time, It also finds a more typical cycle time by excluding unusually long cycles over 50 seconds, showing how a stoppage can raise the overall average. Range. Range measures variation by comparing the smallest and largest values in a dataset. In engineering, it can quickly show whether process results, such as cycle times or temperatures, are tightly grouped or widely spread. A small range suggests stable performance, while a large range may signal issues such as equipment changes or inconsistent materials. The range gives engineers a fast way to compare how consistent processes or machines are. Even when average completion times are similar, a wider range means outcomes are less predictable and may require attention. This matters because inconsistent processes can create queues, disrupt planning, and make improvement harder. Range can be useful, but it only reflects the two most extreme values, so one outlier can make variation look larger than it normally is. Use range alongside other measures and consider the context. Extreme values may point to data errors or real process problems, so treat range as a signal to investigate unexpected variation further. Python code range. Range describes the spread between the highest and lowest values in a process. Engineers use it as a quick way to check variation, such as when reviewing machining cycle times. A list of machining cycle times, measured in minutes, is defined for analysis. These values are used to study how much the process varies and how consistent the cycle times are. The code first checks whether there are at least 2 cycle time observations, since a range cannot be calculated from fewer data points. If there is not enough data, it raises an error explaining that at least 2 observations are required. This prevents later calculations from using insufficient information. To measure variability in cycle times, identify the shortest and longest observed times using the minimum and maximum functions. The difference between them is the range, which shows how far the process varies from its fastest cycle to its slowest. To find the average cycle time, add all cycle times together and divide by how many values there are. The result gives a typical cycle duration for the data. Set 1 minute as the maximum acceptable range for cycle times. If the calculated range is greater than this threshold, the process may have too much variability and should be reviewed. If it stays within the threshold, the process can continue without further investigation. The code summarizes the cycle time data by showing the full list, then reporting the fastest and slowest recorded times. It also calculates the range, which is the difference between those two values, rounded to 2 decimal places. This gives a quick view of how much the cycle times vary. The code reports the average cycle time to show the typical duration of the process. It then checks whether the spread of cycle times is greater than an allowed threshold, and prints whether a review is needed. If variability is too high, the decision is to investigate it. Otherwise, the process should simply be monitored. This script summarizes machining cycle time variability by checking that enough observations are available, then finding the shortest and longest times. Their difference gives the range, while the average provides added context. The script compares the range with a 1-minute threshold to decide whether variability should be investigated or simply monitored, then prints the key results for quick review. Frequency distributions. A frequency distribution groups data by how often values occur, making patterns easier to see. For engineers, it turns large sets of raw measurements into clearer summaries, such as whether cycle times are generally short or long. This helps reveal process behavior and identify potential delays before deeper analysis. Frequency distributions show how data clusters spreads and reveals unusual patterns. When values stay close together, a process is likely stable. When they are widely scattered, it may signal instability from causes such as equipment wear or environmental changes. This matters because two processes can have the same average but very different distributions, leading to different engineering decisions. When reading a frequency distribution, look at where values cluster and the shape of the pattern, not just the average. A balanced shape may reflect normal variation, while a long tail can show rare but important extremes, such as a few very long order times. This helps engineers decide whether a process needs broad changes, like new standards or training, or targeted fixes for specific problems, such as equipment failures. Python code, frequency distributions. Frequency distributions help summarize repeated process measurements by grouping values into bins. Engineers use them to spot performance patterns, such as how assembly cycle times are distributed. We import 3 key Python libraries for data work: NumPy for numerical operations and random number generation, pandas for organizing and analyzing data, and Matplotlib's plotting tools for creating charts that help us understand the data. A small, reproducible dataset is created to simulate process cycle times. Using a fixed random seed, 40 values are generated from a normal distribution with an average cycle time of 5.2 and a standard deviation of 0.45. We create a NumPy array of longer cycle times to represent process delays, then combine it with the existing cycle time data using NumPy's concatenate function. This expands the dataset to include both normal durations and delays, giving a more complete view of cycle time variation. Before processing the data, check that the cycle time dataset is not empty and that every cycle time is positive. These assertions prevent invalid or nonsensical values from being used and stop execution immediately with clear error messages when the data fails validation. Cycle times are grouped using bin boundaries from 4 to 8 minutes in steps of 0.8. Each interval is then given a clear performance label: very fast, typical, slightly slow, delayed, or severe. These labels make the cycle time categories easier to interpret and communicate. Cycle times are grouped into predefined intervals using the pandas cut function, which assigns each value to a labeled bin. Then the labeled results are counted with the value counts method to find how many observations fall in each interval. The counts are kept in label order so the categories remain easy to interpret. Convert the frequency counts into percentages by comparing each count with the total and multiplying by 100. Then organize the results in a summary table with the original counts and rounded percentages. This makes it easy to see how each cycle time category contributes to the overall distribution. The code announces that it will display a frequency distribution table for cycle times in minutes, then prints the table in a readable text format. This helps users quickly see how cycle times are distributed across categories, such as very fast or delayed, directly in the console. Calculate the combined percentage of cycle times classified as delayed or severe by adding their percentages from the frequency table. This shows how many cycles fall into the slowest categories and helps identify performance concerns. Report the result to one decimal place for a clear, concise summary. Set up a clear 7 by 4 inch figure, then create a bar chart of cycle time categories. The categories are shown as labels on the x-axis, while the y-axis shows the unit counts from the summary table. Use steel blue bars to make the chart easy to read. The plot is labeled to make the data easy to interpret. Its title identifies the chart, as a frequency distribution of assembly cycle times, while the x-axis shows the cycle time categories, and the y-axis shows the number of units in each category. The chart is made easier to read by rotating the x-axis labels slightly and aligning them to the right, which helps when labels are long or crowded. The layout is then adjusted so all chart elements fit without overlapping or being cut off. Finally, the chart is displayed for interpreting the frequency distribution of cycle times. This script summarizes assembly cycle time performance using a frequency distribution. It generates mostly normal cycle times, adds a few longer delays, checks that all values are positive, then groups the times into performance categories from very fast to severe. It reports both counts and percentages for each category, highlighting delayed and severe cycles, and uses a bar chart to make the pattern easier to interpret. This helps engineers quickly see where cycle time problems may need attention. Operational performance metrics. Utilization metrics. Utilization shows how effectively an organization uses available resources by comparing active working time with total available time. It can apply to machines, staff, or servers, using time data such as scheduled and operating hours. In Python analysis, this turns raw capacity data into a clear performance measure that reveals gaps between potential and actual use. Python can calculate utilization metrics from structured data, such as production logs and timesheets. Analysts group the data by resource and time, then compare active time with available time to measure utilization. This helps identify underused or overloaded resources, such as manufacturing lines or call center agents. Python is useful because it can process large datasets consistently and reduce manual errors. Utilization must be interpreted in context because higher is not always better. Low utilization can suggest wasted capacity or poor scheduling, while very high utilization can reduce flexibility and make disruptions harder to handle. Analysts should compare resources, watch trends, and use utilization insights to improve staffing, scheduling, and capacity planning. Python code, utilization metrics. This example shows how to calculate machine utilization using a small set of production data. The goal is to make the results easy to understand and help managers use utilization metrics to balance capacity. The script imports pandas for working with tabular data and Matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the script to analyze data and generate plots later on. A simple data dictionary is created to track shift records for 3 machines: mill A, lathe B, and press C. Each machine is assigned 8 scheduled hours, making the structure useful for basic machine utilization analysis. The script stores 2 sets of machine shift data in a dictionary: active working hours and downtime hours. Active hours are 6.2, 7.4, and 4.9, while downtime hours are 0.8, 0.3, and 1.6. These values are later used to calculate machine utilization and idle time. The raw machine data is converted into a pandas data frame, organizing it into a structured table for easier analysis. This table contains each machine's name, scheduled hours, active hours, and downtime hours, which supports later calculations and visualization of utilization metrics. The code first validates that all scheduled hours are positive before calculating utilization metrics. If it finds any scheduled hours that are 0 or negative, it raises an error and stops the process. This prevents invalid data from producing unreliable utilization results. Machine utilization is the percentage of scheduled time that a machine was actively used. It is found by dividing active hours by scheduled hours, then multiplying by 100. Idle hours are found by starting with a machine's scheduled hours, then subtracting the time it was active and the time it was down. The remaining time represents when the machine was available but not in use. The code creates a summary view of the data frame by selecting only the key machine performance columns: machine name, utilization percentage, downtime hours, and idle hours. This makes the results easier to read by focusing on the most important metrics for each machine. The output begins with a short message introducing the machine utilization summary. The summary data is rounded to 1 decimal place to make the results easier to read, then converted to a clean text format without the index and printed to the console. This produces a concise, readable view of the key utilization metrics for each machine. The code finds the machine with the lowest utilization percentage by identifying the row where utilization is smallest. It then creates and prints a message highlighting that machine as the main target for improvement or further attention. A new plot is created at a clear viewing size. Then a bar chart compares each machine's utilization percentage. Machine names appear along the horizontal axis. Utilization appears on the vertical axis, and the steel blue bars make the comparison easy to read. The chart is formatted to make machine utilization easy to interpret. An orange dashed reference line marks the 85% target. The vertical axis is labeled as utilization percent, and the title identifies the chart as machine utilization during one shift. The y-axis is limited from 0 to 100 to match the full possible range of utilization percentages. The code finalizes the chart by adding a legend to distinguish the target utilization line from the actual utilization bars. It then adjusts the layout so the plot elements fit cleanly without overlap, and displays the result for visual comparison against the target benchmark. This script analyzes machine utilization for a small production dataset with 3 machines. It calculates utilization from active hours compared with scheduled hours, estimates idle time after accounting for downtime, and prints a rounded performance summary. It also flags the machine with the lowest utilization as a likely improvement target. Finally, it creates a bar chart with an 85% target line to compare performance visually. Throughput calculation. Throughput measures how much useful completed output a process produces in a given time, making it a key indicator of operational performance. In Python, analysts calculate it by organizing data by time period, counting finished outputs, and comparing them with the observation window. Focusing only on completed items, such as finished units or shipped orders, gives a more accurate view of production capacity, especially when working with large datasets. To measure throughput accurately, first define the time interval, output unit, and process boundary. Use a time period that fits the decision. Keep the unit consistent, and be clear about where the process begins and ends. In Python, timestamps, completion status, and grouping can then be used to count only valid outputs and summarize throughput precisely. Throughput is most useful when viewed alongside demand, capacity, downtime, and quality. High output can hide rework problems, while low output may come from machine downtime or material shortages rather than worker performance. Python helps combine these metrics so you can identify bottlenecks, test changes, and understand where improvements are needed. Python code, throughput calculation. This example shows how to calculate hourly process throughput using completed units as the measure of useful operational output. the data is kept small, so the main idea is clear and easy to follow. We import pandas to manage and analyze production records efficiently, and use Matplotlib's plotting tools to visualize throughput data. Together, these libraries help organize the data and make key trends easier to understand. Create a list of dictionaries to store production data for each shift hour. Each record includes the hour, the production line, and the number of completed units. This structure makes it easy to organize and analyze output by time and line. This segment adds 3 production records to a dataset, 2 for line A at 10 and 11 o'clock, and 1 for line B at 8 o'clock. Each record captures the hour, production line, and number of completed units. Together, these entries help build a list that will later be converted into a data frame for analyzing production throughput. The snippet records line B's hourly output for 3 times, 40 units at 9 o'clock, 44 at 10 o'clock, and 38 at 11 o'clock. These production records provide the data needed to calculate line B's throughput over that period. The production records are first converted into a pandas data frame, putting the data into a structured table for easier analysis. An assertion then checks that the data frame has exactly 8 records, confirming the expected data is present before any further calculations. Calculate total production by grouping the data by production line and adding the completed units for each line. Then count the distinct hours in the dataset to see how many hours of production data were recorded. Throughput is found by dividing each production line's completed units by the number of unique hours observed, giving the average units completed per hour. The line with the highest throughput is then identified as the best performing line by this measure. The output summarizes production throughput by line, measured in completed units per hour. It displays each line's rounded throughput value for easy reading, then identifies the line with the highest throughput as the best performer during the observed period. The data is grouped by hour, and the completed units are summed to show total production for each hour across all lines. These hourly totals are then displayed as a steel blue bar chart, making it easy to compare throughput over time. Set the chart title to Hourly Throughput across both lines so the purpose is clear. Label the x-axis as shift hour and the y-axis as completed units to show time and output. Then apply a tight layout so titles and labels fit neatly without overlapping or being cut off. The final command displays the prepared chart using Matplotlib. The plot shows hourly throughput for both production lines, making it easier to compare their performance across the shift. This script measures production throughput during a shift by organizing completion data, grouping it by production line, and comparing output. It calculates throughput by dividing completed units by the number of observed hours, then identifies the line with the highest performance. It also creates a labeled bar chart showing total units completed each hour across both lines, making hourly throughput easier to interpret. Yield metrics. Yield metrics show how effectively a process turns inputs into acceptable outputs on the first pass. They look beyond total production volume by accounting for defects, rework, or units that fail standards. With structured production data, Python can help calculate these measures and turn raw counts into a clear view of process quality. This helps engineers and managers see whether a process is producing reliable output or simply creating volume with hidden problems. In Python, yield analysis means separating acceptable output from losses, whether in inspected products or error-free service results. By filtering records and grouping them by categories, you can compare accepted output with total input. This helps reveal where and when quality drops occur, pointing to causes such as equipment wear or training issues. Yield metrics should be interpreted with context, not just as standalone numbers. A high yield can still hide slow throughput, downtime, or defects being reworked rather than fixed at the source. Tracking yield over time, such as with Python analysis, helps reveal trends and sudden changes that averages may miss. Consistent context-aware measurement helps teams find quality problems and judge whether corrective actions are working. Python code, yield metrics. Yield metrics measure how much production output is acceptable. Small datasets make these calculations easier to check, and engineers use yield comparisons to evaluate different operating conditions. We begin by importing pandas, a library for working with tabular data. It lets us organize process records and data frames, making the data easier to manipulate and analyze for calculating yield metrics. The data is organized as a list of records, with each record describing one production shift. Each shift includes the shift name and key inspection metrics: units started, units that passed, units reworked, and units scrapped. This structure makes the inspection data ready to convert into a pandas data frame for analysis. The inspection records are converted from a list of dictionaries into a pandas data frame. This organizes the shift data into a table, making it easier to analyze, manipulate, and calculate metrics across shifts. The code first identifies the essential data frame columns needed for the calculations: started, passed, reworked, and scrap. It then uses an assertion to confirm that all of these columns are present before continuing. If any required column is missing, the assertion raises an error and stops the code from running with incomplete data. This check confirms that every value in the started column is greater than 0. It uses the all method to ensure there are no non-positive entries, which would signal invalid production data and make later yield calculations unreliable. First pass yield is calculated for each shift by comparing the units that passed inspection with the total units that began the process. The result is added as a new data frame column and shows how efficient production is before any rework is included. Final yield after rework measures how many items ultimately meet quality standards. It is found by adding the items that passed initially to the items successfully reworked, then dividing by the number of items that entered the process. This shows how rework improves the overall usable output. This calculation creates a scrap rate column to measure quality loss. It finds the proportion of production that was scrapped by dividing scrapped items by the total items started, making it easier to analyze scrap levels. This step totals the key production counts across all shifts. It focuses on the started, passed, reworked, and scrap columns, then adds each column to produce overall counts for each category. These totals give a quick view of aggregate production performance. Overall first pass yield is found by dividing the total units that passed inspection by the total units started. This gives one combined measure of how many units passed on the first attempt across all shifts, making it a key indicator of initial production quality. Overall final yield is found by dividing the number of passed and successfully reworked items by the number of items started. It shows the share of total items that ultimately met requirements, helping measure both the production process and the value of rework. The code prints the heading Yield by Shift to introduce a summary of yield metrics for each shift. This label makes the output easier to read and understand. A new summary data frame is created by keeping only the key columns: shift name, first pass yield, final yield, and scrap rate, This gives a focused view of the main performance metrics without unnecessary details. The code formats key yield and scrap metrics as readable percentages. It converts each value to a percent, rounds it to one decimal place, and adds a percent sign, making the summary table easier to interpret. The code displays a readable summary of yield metrics for each shift. It converts the pandas data frame to a string without the index column, making the results easier to scan. The output shows key percentages, including first pass yield, final yield, and scrap rate. The process reports the overall first pass yield by showing the calculated value as a percentage with one decimal place. This formatted result is placed in a clear message, so the metric is easy to read and understand. The code identifies the shift with the lowest first pass yield to highlight where quality may need improvement. It finds the smallest yield value, matches it to the corresponding shift, and uses that result to guide further investigation into possible quality losses. The code identifies the shift with the lowest first pass yield by finding the minimum value in that column. It then prints a message recommending further investigation of that shift, since it may indicate hidden quality problems affecting production efficiency. The code displays the overall final yield after rework as a percentage, rounded to one decimal place. This gives a concise measure of production efficiency and shows how effective the rework process was. This script uses pandas to check production inspection data and summarize yield performance by shift. It calculates first pass yield, final yield including reworked items, and scrap rate, then reports these measures as percentages for each shift and overall. It also identifies the shift with the lowest first pass yield, highlighting where quality improvement should be prioritized. Process improvement signals. Bottleneck signals. A bottleneck is the step that limits overall performance, even when other parts of a process appear efficient. Metrics should be viewed across the full workflow, not in isolation, because a busy station or fast approval may still leave work waiting elsewhere. The goal is to find where work piles up before a step and where resources sit idle after it, so improvements raise total system throughput. To identify a true bottleneck, look at how throughput, utilization, waiting time, inventory, and cycle time move together. High utilization by itself can be misleading, because queues may result from uneven material release, poor scheduling, demand swings, or weak triage. A stronger signal appears when several metrics consistently show growing work in process and delays at the same step. Improvement should then focus on that constrained step, the flow feeding it, or the rules used to prioritize work. Bottleneck signals show where improvements will help the whole system most. Improving a non-bottleneck may look useful, but it usually will not increase total output. The best interventions target the constraint directly, such as reducing setup time or adding skilled operators, while also checking whether the bottleneck is stable or changes with demand. Python code, bottleneck signals. Bottleneck signals help identify system constraints by comparing flow metrics. Even small tables can make these limits visible, so improvement efforts should focus on the parts of the system that restrict overall performance. The code starts by importing pandas for working with tabular data and the pyplot module from Matplotlib for creating visualizations. Together, these libraries provide the basic tools needed to analyze process performance data and plot bottleneck signals. The process data includes station names for filling, labeling, and boxing, along with each station's cycle time, waiting jobs, and utilization rate. Together, these values describe how long work takes, how much work is queued, and how busy each station is. This information supports performance analysis and helps identify bottlenecks. We use pandas to create a data frame that organizes process performance data in one table. It combines station names, cycle times, queue sizes, and utilization rates, making the data easier to analyze, update, and visualize. Hourly station capacity is found by dividing 60 by each station's cycle time in minutes. The system's overall capacity is the lowest of these station capacities because the slowest station limits total throughput and reveals the likely bottleneck. To find the strongest bottleneck, calculate a signal score for each station by combining its utilization with the number of jobs waiting in its queue. The highest score points to the station where heavy use and a large queue overlap most, making it the most likely bottleneck. This helps identify where improvement efforts should be focused first. This output highlights the bottleneck signal for process improvement. It reports the system capacity as the lowest station capacity per hour, identifies the station with the strongest bottleneck signal, and shows its utilization and queue size. The conclusion is that improvement efforts should focus on this bottleneck before optimizing other non-constraining parts of the system. Create a plotting area with Matplotlib, then use a bar chart to show how many jobs are queued before each station. The station names appear along the horizontal axis, while each bar's height represents the queue size. A clear y-axis label explains that the values are the number of jobs waiting before each station. A secondary y-axis is added to the existing plot using the twin x-axis method, allowing utilization data to be shown on the same graph as the station data. The utilization values are plotted by station with a crimson line and visible markers, and the new y-axis is labeled to show that it represents the utilization fraction. The plot is prepared to make bottleneck signals easy to interpret, especially where high queue levels occur alongside high utilization. Spacing is adjusted so the plot elements fit cleanly, and then the plot is displayed for visual analysis of the process data. This script analyzes production line performance to find bottlenecks. It uses station data such as cycle time, queue length, and utilization to estimate each station's hourly capacity, then treats the lowest capacity as the system limit. It also scores bottleneck signals by combining utilization and queue length, identifying the highest scoring station as the main bottleneck. The results and a simple chart help show where improvement efforts should be focused. Downtime decision signals. Downtime is more than lost production time. It signals where a process may be weak or unstable. It can come from failures, shortages, or outages. But the real value is in understanding its patterns and effects. Long stops may point to maintenance needs, while frequent short stops may reveal coordination problems. By connecting downtime to factors like time of day or product type, managers can take more targeted action. When reviewing downtime, separate the visible symptom from the real cause. High downtime may look like equipment failure, but it can also come from upstream delays, quality checks, scheduling problems, or related system issues. Comparing downtime with utilization and throughput helps show whether it is actually reducing output, or whether the time could be used for training or maintenance during low demand. Downtime metrics are most useful when they help managers decide where to focus improvement efforts. Because organizations cannot fix every issue at once, they should prioritize downtime that strongly affects performance, cost, safety, or customer service. These signals can point to needs such as better monitoring, retraining, faster changeovers, or infrastructure upgrades. The goal is to identify where reliability is being lost, and choose actions that strengthen process resilience and support organizational goals. Python code, downtime decision signals. Patterns in downtime help identify where practical improvements are most needed. Even small datasets can point to operational priorities when the metrics are interpreted in context. The script begins by importing pandas for working with structured data and Matplotlib's plotting module for creating visualizations. Together, these libraries prepare the environment for the data analysis and plotting tasks that follow. We create a small dataset to summarize shift downtime activities. Each entry represents one downtime cause and records the cause, the number of events, and the total minutes lost. This simple structure makes the data easy to turn into a pandas data frame for analysis. The records are converted into a pandas data frame, turning the list of dictionaries into a structured table with rows and column headers. The shift length is then set to 480 minutes, which supports later validation and downtime calculations based on the correct work shift duration. Check that the downtime data is not empty before using it. Then confirm that total downtime does not exceed the total shift time, so the data remains realistic and within the expected operating period. To analyze downtime, first compare each cause's minutes with the total downtime to see its relative impact. Then, find the average downtime per event for each cause to tell whether problems are frequent and short, or fewer and longer. Causes with an average of 40 minutes or more are classified as long, while the rest are classified as recurring, helping prioritize the right response. The process ranks downtime causes by minutes lost, starting with the largest problems. It then totals all downtime minutes and compares that total with the full scheduled shift time. The resulting downtime rate shows how much planned operating time was lost, helping assess overall efficiency. The code summarizes downtime by showing total minutes lost during the shift and the downtime rate as a percentage of scheduled time. It then introduces the main causes of downtime and their decision signals, preparing for a closer look at each cause's impact and recommended action. The code goes through each downtime record and pulls out the cause of the issue. It then builds a short message showing the cause, total downtime in minutes, and the signal type, which identifies whether the issue comes from long events or recurring problems. Each message is printed as a concise summary for review. The code finds the top improvement priority by taking the downtime cause with the highest total minutes. It then chooses the recommended focus based on that cause's signal. A long signal points to maintenance, while any other signal points to coordination. Finally, it prints the priority action and the cause that needs attention. This creates a simple bar chart to compare downtime minutes across different causes. The plot uses a 7x4-inch figure, steel blue bars for clarity, a title describing downtime decision signals by cause, and a y-axis label showing that the values are measured in minutes. The code improves the chart's readability by rotating the x-axis labels and aligning them to the right, which helps when labels are long or crowded. It then adjusts the layout so the chart elements fit without overlapping or being cut off, and finally displays the plot for interpreting the downtime data. This script analyzes manufacturing shift downtime to identify where improvement efforts should focus. It builds a small dataset of downtime causes, event counts, and minutes lost, then checks that total downtime fits within the shift length. It calculates each cause's share of downtime, average time per event, and whether the issue is mainly long-lasting or recurring. After ranking causes by total minutes lost, it reports the downtime rate, recommends a priority action such as maintenance or coordination, and shows the results in a Pareto-style bar chart for easier decision-making.
Sustained improvement signals. Sustained improvement signals show whether a process change is becoming a stable part of normal operations rather than a short-term gain. Managers look for consistent performance over time, such as fewer defects across several production cycles or steady output across shifts and conditions. These signals help separate random variation from real process learning, guiding decisions about whether to standardize the change, invest further, or keep investigating. Sustained improvement means several key measures improve together and remain stable over time. Higher throughput or utilization is not enough if defects, downtime, or maintenance problems increase. Real progress produces more output with less waste while maintaining reliability under normal conditions, such as faster lab results with low errors or a warehouse layout that keeps accuracy and efficiency high beyond a supervised trial. When judging whether an improvement is sustained, look beyond the numbers to the human and organizational conditions behind them. A change is not yet robust if it works only when an expert is present or demand is low. Stronger evidence comes when multiple teams repeat the results, procedures are documented, and gains hold during normal disruptions. These signals guide whether to standardize, expand, or further refine the solution. Python code. Sustained improvement signals. Stable results require repeated evidence, not just one measurement. Even small datasets can show whether improvement is consistent, and the right metrics help guide practical engineering choices. We import pandas to work efficiently with tabular data, and Matplotlib pyplot to create visualizations in Python. Together, these tools support data analysis by making it easier to manage datasets and view performance trends. We create a dictionary to store 6 days of performance data. It records the day number, daily throughput, yield rate, and downtime in minutes. This organized structure makes it easier to analyze how performance changes over time. We use a pandas data frame to organize performance records in a structured format. This makes the data easier to analyze, such as calculating averages or comparing time periods, and prepares it for studying sustained improvement signals. The code first checks whether the data has at least 4 observations. If not, it stops the analysis and raises an error because too few observations may not reliably show sustained improvement. To compare performance over time, we average the numeric values from the first 2 rows to create a baseline, then average the last 3 rows to represent recent performance. Comparing these 2 summaries helps reveal whether the metrics have improved or changed. The code measures performance improvement by comparing recent results with baseline values. It calculates the increase in throughput, the gain in yield rate, and the reduction in downtime. Together, these differences show how much operations have improved over time. To judge whether recent performance has improved consistently, we look at the last 3 days of data and compare them with earlier baseline averages. Throughput and yield must stay above their baselines even at their lowest recent values, while downtime must stay below its baseline even at its highest recent value. Together, these checks show whether the recent gains are stable rather than isolated. The code identifies sustained improvement only when throughput, yield, and downtime are all stable. It checks these conditions together using the all function,
and returns true only if every condition is met. This tells engineers that recent performance gains are consistent and reliable. The output summarizes recent performance against the baseline. It reports baseline throughput, recent gains in throughput and yield, and the drop in daily downtime, using rounded values for readability. It also shows whether the improvements are sustained, meaning recent results consistently beat the baseline across all metrics. Create a plotting canvas with a figure and axis. Then plot throughput against production day using circular markers. Label the horizontal axis as production day and the vertical axis as units per day, so the chart clearly shows how throughput changes over time.
A second y-axis is added to the existing plot using the twin-x method, allowing data with a different scale to appear alongside the throughput data. Downtime minutes are then plotted against production days on this new axis, using red square markers for distinction. The new axis is labeled downtime minutes, so the added data is clear. The plot is finalized by adding the title Sustained Improvement Signals, adjusting the layout so elements do not overlap, and then displaying the figure. This makes the visual easier to read and supports assessing sustained improvement over time. This script checks 6 days of production data to see whether performance has genuinely improved. It compares the first 2 days as a baseline with the most recent 3 days, looking for higher throughput and yield, along with lower downtime. If the recent results consistently beat the baseline across all metrics, it reports a sustained improvement signal. It also prints the key changes and plots throughput and downtime over time to show the trend visually. In this lecture, you learn to first, compute descriptive measures for production and process performance data. Next, calculate utilization, throughput, yield, and downtime metrics in Python. And interpret metric results in relation to process improvement decisions. In the next lecture, Lecture B, we will go over inventory and queues.
Thank you for your attention. See you all in the next lecture.